start. Okay, so good afternoon, everyone. Welcome to our April NITheCS Mini-School. And this will be a mini school because April has only 3 Tuesdays. Yeah. So, but I'm very happy that to be able to introduce to you Professor Uwe Jaekel. Some of you might have met him before because I think 2 years ago he was one of the speakers at the NITheCS summer school, where he spoke on. I think he gave an introduction to quantitative finance for physicists. Yeah. So Uwe studied astrophysics, has a PhD in astrophysics from the university in Bonn in Germany. After his PhD, he moved to the research center in Jülich. And I think 5 or 6 years later, he started working for NEC, which is a Japanese company that produces, among other things, high-performance computers. And he was developing software algorithms for them. And after a few years at NEC, he became professor at the University of Applied Sciences in Koblenz, where I think he's a professor for technomathematics, if I remember correctly. Uwe, please correct me if I diffuse fake news. So, and I'm very happy that Uwe agreed at short notice to give us this mini school, because last week or last month we had a mini school on models or epidemiological models for COVID, and we encountered Monte Carlo methods. But some comments from the audience indicated that maybe there was a market for a mini school on introductory aspects of Monte Carlo methods. Yeah, so the short months was then the perfect setting to start the introduction to Monte Carlo methods, and then depending how it goes, we might have at some other stage have another mini school on more advanced methods. So Uwe, we are really very grateful for your time and for agreeing to be with us for these months. And so are, I think, all our participants. So Uwe, if you would like to start sharing your screen
yes,
and start the presentation, and while you do that, I will do just the usual recommendation to please pose your questions in the Q&A, and Ilya, who all of you know by now, will collate the question and moderate them at the end of the talk or during the talk if there are some important and urgent questions that come up. So Uwe, thank you very much. You are welcome to start.
Yes. Okay, thank you very much. 1 second, I want to share my screen. Okay, you see a blank screen, hopefully now?
Yes, yes.
More or less blank?
Yeah, yeah.
Yeah,
and I think it's notability.
Yes, it's notability indeed, yes. So thank you very much for the introduction, which was almost correct, but I'm not working in technomathematics, but or formally I don't have an appointment as a professor in technomathematics, but in mathematical finance.
Okay, sorry.
Yeah, that's not bad. Maybe technomathematics may sound more honorable to many, but mathematical finance is also quite interesting, and Monte Carlo methods are a very important topic in this field as well. And by the way, for the parts of the audience, sorry, I don't want to waste the time, but it's snowing in Germany now. I could show you some snow in spring in Germany, which is not quite usual. But we don't want to waste. I don't want to waste your time. Maybe I can do this in the Q&A session if you want to. If it's demanded. Yeah, so thank you very much for showing up in this Zoom session on Monte Carlo methods. Francesco said it's on quite short notice, so it's not, yeah, it's improvised partially, but I have prepared a few things which I will make available later. So for instance, Python, some notebooks, and Francesco will tell me where I can put it. Also, I have some lecture notes that I will have to revise, but I can make this available as well. So this is on Monte Carlo methods. And I understood that the audience has a variety of backgrounds. So not all of you are physicists or mathematicians, but you're also coming from biology, chemistry, and I think this is correct. So please correct me if I'm wrong. We have 3 sessions. And the first one will be for the introduction. If this is too slow or too fast, it's probably, if it's anything, it might be too slow, but just tell me what's missing and what you would rather like to know than the primitive or rather simple stuff that I will tell you today. So this will be on Monte Carlo methods. My plan is today I will show you some one-dimensional basics and some heuristics, some basic facts about Monte Carlo methods. And next week we'll make it a little bit more sophisticated. How we can improve the accuracy of the methods. It's basically variance reduction, and in the last session in 2 weeks I will tell more about Markov chain Monte Carlo methods, which are closer to the to actual and current research topics, and where you can really do some more sophisticated stuff. So today is more or less about simple, basic Monte Carlo methods, and I guess more or less you will, most of you will have an idea what Monte Carlo methods are. Francesco told me that that it came up in the previous summer school, mini school. So what are Monte Carlo methods? And in order to be as flexible as possible, I will give a pretty generic answer. It's solving problems using random numbers. I emphasize that random numbers sound like statistics and probability theory, and I want to emphasize it's not only on statistics and probability theory. More or less, you are always solving okay, sorry, I was distracted by another window. I have to close it again. Sorry, now I lost it. So I want to emphasize it's not only about getting, of course, it's mostly on computing expectations, but quite a lot of sophisticated topics can be formulated as expectation values, even though the questions are deterministic or sound deterministic. So we want to solve often deterministic problems using random numbers. So this can be, for instance, integration. can be computation of expectation values. But this is more or less the same as integration. It can be solving partial differential equations. And as I told you, I'm a bit flexible. If you like, I can tell you a little bit more about partial differential equations next week. I think the third week should be exclusively for Markov chain Monte Carlo methods, because the problem is complicated enough. But if you want to hear more about partial differential equations, I can tell you a few words about this next week. Just let us know what you would like to hear. So, and we start with a famous example, an example probably most of you know. And I use quotes, computation of pi. If you have a statistical background, you usually don't do a computation, yeah, but you do an estimation. So you don't compute an expectation value, but you can estimate an expectation value. And actually, we want to get pi as an estimation for an expectation value. And I guess that many of you have seen this example. Probably I cannot get any feedback, right, Francesco?
Uwe, people can comment in the chat or in the Q&A. And if there is some really urgent question, they can raise their hand and we can allow them to talk.
Yeah, okay. So please let us know, let Francesco know, or let me know if this is too well known. But I'll start with that. Yeah, with this simple example, we want to get an idea what is pi. What is the value of pi? Assuming that that we all know that pi is the area of the unit circle. And the unit circle is a circle with radius 1. So we have radius 1. In mathematics, we usually don't use units. Yeah, so if it's 1 meter, we have pi square meters as the area. And how can we compute pi with Monte Carlo methods? So what we can do is we draw random numbers from, we draw a random number on the x-axis. Let's say this is 0.71 something. And we draw a random number on the y-axis, and let's say it's here. So we have a y1, 0. Let's say this is, I don't want to do a real computation. Let's say this is 0.951, because then I'm pretty sure that it's outside the circle. And we say we ask the question, is this inside the unit sphere? So we have a random x coordinate and we have a random y coordinate. And we ask, is this inside the unit sphere? And the question here is obviously, so this is the unit sphere. It's not. In this case, no. This is a miss. We didn't have a hit, we have a miss. And we do this with a pretty large number of random numbers. And so all these random numbers are between 0 and 1. And these are uniformly distributed. So the x values and the y values are both uniformly distributed. And now we want to know what is the surface of this quarter. In this case, we draw the, we have embedded the part of the unit sphere, one quarter of the unit sphere, and this is embedded into a unit square. We know that the area of the unit square. This is an area equal to 1. And now, what is the number of, what is pi over 4? So that's the ratio of the area of the, so the, if these points are uniformly distributed on this, on the sphere, then this will be the number of hits, the ratio of the number sorry. So this is first, this is the area of the unit sphere, or of a quarter of the unit sphere, or 1/4 of the area of the unit sphere. Divided by the area of the unit square. And if the random draws, so let's assume these are dart small arrows that we throw into this unit square board, the number of hits will be proportional to the area of the unit sphere, and the number of misses will be proportional to the total available area. So this will be approximately the number of hits divided by the number of trials. Let's say by the divided by the number of throws. So this is a well-known algorithm for the computation of pi, and I will show you an implementation on Python. For this, I have to share another screen, sorry. So I hope you see your notebook now.
Yeah, we can see it, Uwe. Thank you.
Yeah. Okay. So what we do here, I have decided I use, let's say we have 100 points. So we draw 100 points from the unit sphere from a random distribution. I don't want to go too much into Python, but this is how you do it in Python. This rand_n, part of the NumPy library, this draws n uniformly distributed random numbers. Yeah, uniformly distributed means here from such an interval. This is a uniform distribution of random numbers over the units, over the unit interval 0 to 1. And we draw another set of 100 random numbers, independent from that, hopefully. We'll look into this a little bit later today. And this will be the y coordinates. So this will be the x coordinates, this will be the y coordinates, and then we make a logical test. So we test, will this, what is the equation for the unit circle? X squared plus z plus y squared is less than 1. squared, but this is 1 again. We test whether it's inside the circle. So if the answer is yes, it's inside the circle. If the answer is no, it's outside the circle. And for the rest, we don't. So this is a little bit Python stuff, how to visualize it. We color the misses in orange. We color the hits in blue. And it looks like this. So here we have 100 data points. Hope this is visible. Good enough. Let's see. Okay, and here we have 76 hits and 100 attempts. So our estimation for pi will be 3.04. Plus minus something. I will talk about the error a little bit later. And the plus minus, so this is the standard error, which we will discuss in a few minutes. I also get an error estimate. That's also a nice thing of the Monte Carlo methods. I get an error estimate, which is probabilistic by nature, but in 68% of the cases, the true value, let's say it a little bit oversimplified, in 68% of the cases, our real pi will be in the interval specified by this. And this is correct. We know the exact value is 3.14 and so on, 159 and so on. And we see that it's in this interval. Let's do it with 1,000 data points. And we get a better estimate with a better error. Here you see definitely the hit and miss structure. Let's go to 10,000 data points. And we already get a pretty decent approximation to pi. So this is approaches 3.14. But of course, we don't get it quite right. And what the Monte Carlo method will show us, and probably is, it might also be known to you already. If we want to increase the accuracy, let's say we want to have one more digit here in the error. So it should be closer to 3.14. And here this means it could also be 3.14 or 3.18, right? In order to get one more digit, I have to increase the number of attempts by a factor of 100. Because the accuracy is, we will see why this is the case in a few minutes, hopefully. We have to increase it by 2 orders of magnitude in order to get an estimate which is more accurate by 1 order of magnitude. Because we have this square root of n law. So if I'm using, yeah, and you see, it's almost exactly the same estimate, but this time we have improved the accuracy by an order of magnitude by increasing the number of evaluations by a factor of 100. So our computation took 100 times longer. We get a more accurate result. So this is pretty close now. And the details depend on the random numbers. So we don't have a deterministic result. So here now the estimate is a little bit different. And a little bit different again, but we see that the first 3 digits are okay. So that's basically the first simple Monte Carlo algorithm that is probably well known to you. So unfortunately, now we have to do a little bit of notation and to agree on the statistical background. and mathematical background knowledge that we assume here. Okay, yes, I think you see the correct things. So I assume that you all have an idea what a random variable is. So in principle, a random variable is a function from a measurable space into the real numbers. Formally, it's this one. So x of omega is some event that has happened, and this is a real number. And this real number, it can be anything. For instance, if you're rolling dice or rolling a die, it will be a number between 1 and 6. So 1, 2, 3, 4, 5, or 6. It can be a continuously distributed variable. And just for the notation, not all of you are mathematicians, and the physicists don't like this too much, I think. But the random variables will be capital letters, and the values that are observed will be small letters. Yeah. So a random variable doesn't have a value yet. It only gets a value after one of these events has happened. I think you have some intuitive understanding what a random variable is. So I won't go into the into details. And these random variables can have distributions, probability distributions, and could be, for instance, normally distributed random variable. If we have discrete variables, it can be these will attain discrete values. And I just want to review a few things. So what do we need for the Monte Carlo methods? So first thing we need is the law of large numbers. So let's assume we have random variables x1, x2, and so on. Xn. And n is undetermined so far. What the message of the law of large numbers is if we take the average of these numbers, so 1 over n times x1 plus x2 plus and so on up to xn. This converges in distributions, so that this is the weak law of large numbers. The strong law is almost surely. We don't have to know this. This converges to the expectation value of x. And what we assume is that these are independent and identically distributed variables. So these are all random variables coming from the same distribution. That's our basic assumption. So independent, I don't want to write it down in order not to waste too much time, independent and identically distributed. It will be in the written notes that I will distribute later. Or Francesco can send it to you. Sorry, my notes are switching off. Okay, so that is the first law, which is very, very important for us. What is an expectation value? We will discuss it a little bit later. Just want to write down what we assume. And another essential ingredient is the central limit theorem. So what is the message of the central limit theorem? It's one formulation is also a message about the average. We assume that these random variables are identically distributed and independent, and this independence is very important. It will be it will cause a lot of trouble if the values are not independent, and we'll have to discuss this later in the context of Markov chain Monte Carlo methods. So if you don't have a statistical background, stochastic independence is very important. What stochastic independence means, I will discuss in a minute. So one of the things is that sorry, this is for n approaching infinity. So the central limit theorem says that this the average, again, will not only converge to the expectation value, but if we take the average, this will approach a normal distribution. And what will be the normal distribution? So the average, it should converge to the expectation value of x. And since all the random variables are from the same distribution, IID, identically distributed, this will be the expectation value of x. And then we have a thing called the variance, sigma squared. And what is the variance? The variance is just the, so that's the variance of the variable x1, or x2, which is the same random variable, because they are all identically distributed. And the definition of the expectation value is just, or the definition of the variance is the expectation of the quadratic deviation from the mean. So we can write this as, or this can be rewritten in this way. And due to the linearity of the expectation value, we can also write it in this way. So the expectation value of x squared minus the expectation of x squared. So what we need now is a definition, or I want to make sure that we all know what I'm talking about. So what will be the expectation value? So let's assume that x is a discrete variable. So the random variable will be will have one of a small set of values. Let's say it's from x1, x2, x, let's say capital K. And one of these events occurs with probability P1, P2. So this will be the probability of x1. This will be the probability of random variable has the value x2, and up to pk. Yeah? So the probability that x of omega will be equal to xl, this is just pl. What is the expectation in this case? The expectation is defined as the every possible outcome xl, and this is one of k events. Yeah, the first possible outcome is x1, last possible outcome is xk, and we have to weight it with the probability of this outcome. A simple case, let's say rolling a die, a fair die, which has the events are 1 through 6, and all probabilities are the same. And since they have to sum up to 1, the probability will be 1 over 6. So in this case, the expectation value will be 1 over 6 times 1 plus 2 plus and so on plus 6. And you can compute that this will be 3.5. And by the way, it's additive. So if we roll 2 dice, the expectation value will be 7. So you can compute the standard deviation if you like. We don't do this exercise, just to show you that this is a simple thing. Now we want to know what is it for a continuous variable. That the expectation value is is the following thing. I will assume that the continuous variable can have a real number value, and formally we say it will it can be between 0, minus infinity, and plus infinity. There are distributions which are ranging only from let's say 1 to infinity, but then the probability that it has a negative value will be just 0. So there's no restriction. If I can write it always in this way. Yeah, so then we have the possible outcome x, and we integrate over all possible outcomes x and weight it with a density function. So P of X will be the density function. And I hope you are familiar with the density functions. Most of you know the Gaussian density function. And the idea of a density function is that if we have a small interval x ranging from x plus to x plus delta x, the probability that x will be, or that the random variable will be in x to x plus delta x in the interval. This is just the integral from x to x plus delta x times the probability density function of x. And this is, if delta x is a very small number, this is pretty close to P of x times delta x. Now, what we also need is the cumulative distribution function. So this is the probability density, PDF, probability density function. Another important thing that that we have to know is the CDF, the cumulative distribution function. And this is the probability that the random variable takes a value. So a small letter x always means that one given distinct value, and x is the random variable. So the probability that the random variable will have a value less than x, this will be just minus infinity to x. And then we integrate the probability density for instance, we know that let's assume that this is a Gaussian distribution. Then we know that it's exactly symmetric around the average, or around the expectation value. This is mu. So this will be the cumulative distribution function. This will be 1/2. And the further we go to the right-hand side, the closer we come with the CDF to 1. So this will be the PDF. And the CDF, that will always be something between 0 and 1. And so in this case, it's here we have a turning point at mu. It looks like somewhat like this. So this will be the CDF. Okay. So this is basically what we assume about the mathematical background and the statistical notation. Francesco, shall we have a short break and ask whether there are questions?
Yes, sure, Uwe, we can do that. Ilya, would you like to guide us through the questions that we already have?
Yeah, we have a couple of questions in Q&A. Okay, so the first question was related to the algorithm of calculating of the pi, I assume, and it's related to the fact that somebody is asking why it's an x squared plus y squared smaller than 1, not smaller or equal to than 1.
Yes, this would be almost the same algorithm. The answer is, so it doesn't make it. The answer is it doesn't make a difference. It's a good question, but it doesn't make a difference. Yeah? So we get more or less the same estimate. I wondered whether I should write it down here, but the thing is, the probability that it will be exactly on the boundary is extremely slow. Actually, it's 0. the probability that we hit the boundary exactly is exactly is zero. Yeah? So if you zoom into it, sorry, I thought you could see it, but I didn't change the screen. Sorry. So the question was, I wrote is less than 0. I could have written it's less than or equal to 0. Sorry, to 1. It's basically it yields the same result, or virtually the same result, because we have it's extremely unlikely that we exactly hit this boundary surface where it's exactly equal to 1. So mathematically, this event, that a randomly selected point on the units on the sphere hits exactly the boundary is mathematically 0. So we will, the mathematicians say, almost surely we will not hit the boundary. I hope this answers the question.
Yeah, I also hope so, and I completely agree with you. And I think it's called something like set of the measure 0 or something like that.
Yeah,
that
right.
will be
the boundary. The boundary is a set of measure 0. That's exactly the.
Okay, and the second question is more related to your handwritten notes and your notations. And the anonymous attendee is asking, I'm getting a bit confused with the difference between capital X and small x, just as they display in writing. Did I understand correctly that for the law of large numbers, we were talking about small x's, but for the central limit theorem, the expectation values are the big x's? And we're seeing your Jupyter notebook.
Yes. I'll go back to my notes. Yes. I wanted to avoid to go too much into the details. So yes, this is a random variable, and you could read it this way. Actually, it makes sense in both formulations. You can formulate it with capital and with small x's. So assume that we that these are random draws that actually have taken place. So x1 is in a way the random draw that has not taken place yet. And I just want to give some physical or mathematical intuition. Yeah, and so before we do make any measurement, we can say this is an uncertain variable, and then an event takes place. So this is usually called omega, and then we get a value x1, and the value that we have drawn, that will be I write down in a small letters. And when we if we sum up all these small letters that we have observed, and take the average of these small letters, they will be pretty close, not exactly the expectation value, but they will be close to the expectation value. And if we and the law of large numbers says if I do have a very large number, I come arbitrarily close to the expectation value. Actually, in probability, it means that the probability that I have a large difference is getting arbitrarily small. So I can say, for instance, I can specify a probability, and then I say the prob. I will for every limit. Let's say this is my sorry. I cannot switch back. I will just share the whole screen. I think that's easier. So I think now you see my complete desktop, right?
Yes.
So I can specify let's say an acceptable error, and the probability that my measurement of n will be larger than this acceptable error. This will be arbitrarily small, becoming arbitrarily small. And the same is with the central limit theorem. I've written it this way because the average is a random variable. So if you have different realizations, if you make one measurement of n variables and then you repeat it, you will get another average. Yeah, so same here. If I do it with a smaller number, so this is one measurement. There I get an average of 3.16. That will be my average value of pi. I do it again, and it will be 3.12. That's why people say this is all the average is also average of n variables is also a random variable. But again, if I do it for a concrete realization, so I actually perform this experiment, this will be really close. We will see it in a few seconds. This will be really close to a normal distribution.
Okay, thank you. And there is no more questions, so we could probably continue.
Okay, yeah. So, yeah, actually, I'm too slow. Probably I should go to slides next week, but nevertheless, okay, I'm now here with that. So the first ingredient. So what we have here is a basic Monte Carlo method, and the first ingredient that we have is obviously we need some random numbers, and here we have uniform random numbers. We will use other distributions later, but how do we get the uniform random numbers? So first of all, you should know that random numbers are valuable resources. So it's a quite useful thing if it's only for Monte Carlo methods. So if you have a possibility to generate real random numbers, then you should be happy because they are really hard to generate. You may know that Laplace has already thought about rolling die. If you have any all complete information classically, all classical information about the initial conditions, the future should be deterministic. And so in principle, someone who has all information, all classical information, should be able to predict the outcome of rolling a die. But classical theory is not completely correct. And there are perturbations that you don't know. There are several methods to try to compute real random numbers using thermal noise and so on. So they are physical random number generators. So this is random number generator. And this is a very, very, very valuable resource. And you may know that real random numbers it's not easy to get real random numbers, but in one field of physics there are almost by not by definition, but they show up in a way that that has puzzled Einstein, and that's quantum mechanics. So the only source, to my knowledge, the only real source of random numbers is quantum mechanics, and the best random number generators are actually quantum mechanical random number generators, and Francesco and Ilya can tell you more about it. And of course, these are pretty expensive resources. Then there are pseudo-random number generators. And pseudo-random numbers, these are the random numbers that are usually used in Monte Carlo methods. I think there has been some recent progress on physical random number generators. Francesco and Ilya may know more about it. Maybe we can discuss this later. So I think there is some interesting progress in this field, but usually people are using pseudo-random number generators. So these are actually deterministic. But they look random. So they appear random and pass several statistical tests. For randomness. I will not talk about the kind of tests here, because that would take too much time. But I can show you something that can happen if you don't are not careful enough. I've prepared that for. Sorry, I'm not very good at switching windows. So back to my notebook. I don't go too much into the random number generators here, but I want you to be aware that things that bad things can happen. One of the first random number generator was looked like this. So you need two numbers, and one of the numbers is 2 to the power of 31. You need another number. So what we want to have is a random number that is uniformly distributed. We want to use it for, let's say, for the Monte Carlo method that we just looked at for the case of computing pi. And now let's assume that we want to compute the random numbers this way. it looks like this. We have this fixed number 2 to the power of 31 and the number 2 to the power of, that is, I forgot, I think, that should be 2 to the power of 15, no, 16, minus 1, plus 1, I think. And I take this number and multiply it. I initialize the random number generator with 1. And the idea is to generate random numbers or random numbers that appear random between 0 or let's say 1 and 2 to the power of 31. And what I do is I take the previous number and multiply it with a large number, with this large number. And if I do this again and again, of course, the number will grow and grow and grow and grow and leave this interval. But I say this will be the largest number possible. So I take take it modulo this large number. So I take the integer remnant after. So what remains of the number after an integer division. So this is the modulo operation. So like 9 modulo 7 is 2, yeah, because if you divide 9 over 7, you have a remainder of 2. So you take this remainder. And what you see is that then I will get a random distribution starting with 1. The first pseudo-random number will be 1. The next pseudo-random number will be this one. And then it starts to be randomly distributed over the interval. It looks quite nice, like a nice flat random distribution, and you can show that it's all numbers have the same probability. And if I do this, sorry, this is the x's are different here, so the x-axis is longer than the y-axis. But this is what the distribution looks like. If I take the first component and plot it with the second component, so the first will be, sorry, I map it then to the interval 0 and 1. So far I have values between 1 and this one. And now I want to map it to a number between 0 and 1 by dividing it by this large number, 2 to the power of 31. And what I get then is randomly looking numbers between 0 and 1. And what I plot here is the randomly looking number un versus the randomly looking number un minus 1. And if these are really independent, this should fill nicely the unit square. So this looks more like a unit rectangle, but you see it's filled nicely. So very good. And it was this random number generator was actually used in the 70s on the IBM mainframe machines. It was not the fault of IBM, I think, but it was a quite popular random number generator. It was also very convenient, and the machine could compute it very fast due to the nature of these numbers. So everything was fine. But so this is the sequence un versus un plus 1. So I draw the nth random number, take this as the x component, and then I draw another random number from the same, the next random number from the sequence, and plot it. And you see, I can observe everything. A large x value followed by a small x value followed by a large value of y, a large value followed by a small value, large value followed by a large value, and so on. Yeah, so you see, this looks quite nice, quite random. But now I can take the list of 3 subsequent numbers. So, and then things don't look nice. And this was, it was discovered after this algorithm had become quite popular. But you see, all these, a sequence of 3 consecutive random numbers, these are all on 15 hyperplanes. Oh, sorry, on 15 planes. all these random numbers, from some perspectives, these look quite randomly distributed, but you see there are gaps. So actually they are not really randomly distributed, but they are lying on planes. So this is a bad thing that should not happen. And nowadays it's quite well investigated topic. There are more complicated random numbers. There are better choices for random numbers. In my written notes, you will find another iteration. But what you should remember, these are actually deterministic numbers, and they should pass a number of tests. So this is one of the simplest possible tests that should be passed, and this fails, of course. In most modern random number generators, this problem is more or less solved. So all the random number generators that are used in Matlab or Python or R in most computer languages or in most random number libraries are very well tested, and they don't show this phenomenon. So one of the most popular random number generators is the so-called Mersenne twister, and this is a very nice random number generator. But you should never forget that these are actually deterministic sequences, and if you are dependent on real random numbers, then you should not use, for instance, the Mersenne twister. It's not cryptographically safe, because you can predict, if you know a few of the random numbers, you can predict the next one. So this can happen, and you should take care. But nevertheless, the random number generator, the Mersenne twister, is very good for some numerical applications, and in particular for Monte Carlo methods, because there are no obvious correlations like this here. So then I want to show the central limit theorem at work. So now let's assume that we have a decent random number generator. And here I'm using the one from Python. Actually, I don't know what it is, but I think it's the Mersenne twister that I've mentioned previously. I know that the default random number generator in Matlab is the Mersenne twister, and yeah, Mersenne twister is a very popular choice. So what I have here is I draw 100,000 of these random numbers, and I plot a histogram of these random numbers. So I do this oops. Oh, sorry, I'm already there. So here I have my random number generator. Just missing the results. Okay. Okay, here we go. So this is one uniformly distributed random number, and now we want to generate other distributions. And one way is just adding up the random numbers. But then we know that adding random numbers, we know that statistically this will, the resulting distribution will be the convolution of the distribution with itself. What would you, unfortunately, I cannot ask the audience. Usually I would ask the audience, what would you expect? What would is the distribution of two of these if they are independent and identically distributed? what is the distribution of 2 of these random numbers? Perhaps you can think for a second for yourself. What would you expect? So I wrote the function such that a number of these are added. So now, if I move the slider to 2, it will show the resulting distribution for two uniformly distributed random numbers, and it looks like this. So it's really a triangle. It's linear on both sides. It has a distinct peak, which becomes more prominent if I increase the number. You see, it almost looks like a perfect triangle, of course, with some statistical fluctuations. This is the distribution resulting from adding 2 uniformly distributed random numbers. And the probability to have one very small value is pretty small, because in this case, so why is it increasing? In this case, you have both of these random numbers have to be quite small, and that's not as likely that as 2 random numbers that have intermediate values. You have more possibilities to produce one value around 1, because that can be 1/2 plus 1/2 is 1, 0.3 plus 0.7 is 1. So you have quite a lot of possibilities. And for instance, to observe the value of 0.01, you have to have 2 small values. So it should be plausible that this peaks in the middle. And again, if you want to have 2, if the sum should be something like 2, both have to be very close to 1. And that's again pretty unlikely. And if you add 3 random numbers, then it's starting to look smooth. 4 random numbers, 5, and so on. And by the way, if you add 12 of them, then you are exactly then you have variance 1, because the variance of the distribution you can compute is 1/12. So if you add 12 of them, they have variance 1 and the standard deviation. So if you don't have any idea, and if all you have is a uniform random number generator, and you want to compute, or if you want to have a good approximation of Gaussian of a normal distribution with standard deviation 0 and variance 1, then you can just add up 12 of these random numbers. Of course, you see it's centered around 6, because there are 12 of them. Every one of them has an expectation of 0.5. So you have to subtract 6, but then you have an almost, you already have a very good approximation of the Gauss distribution. And the more you take, the more summons you take, the more random numbers you take, the closer are you coming to the Gaussian distribution, to the normal distribution, standard normal distribution. Sorry, not standard. This has a different variance, but you are approaching the normal distribution. Yeah, and speaking of that, oops, sorry. Speaking of that, you can spot the error. I've made one mistake. Does anyone spot a mistake here? Maybe you can write in the chat. Okay, so actually this is not what I have here is the mean, and the mean is converging to the expectation value, and so I had another formulation in mind. So you have to the error has to be divided by n. So that's for those who know a bit more about the mathematics. So this is the variance of the mean. You have to divide it by n. So that was my fault. It should be something like n, because due to the law of large numbers, you know that this has to approach the expectation value, but it can. So this must come closer to the expectation value, and therefore you have to divide it by n. Yeah? Oh, sorry, you couldn't. No complaints. Sorry, you could not. Forgot to share the other screen.
Yeah, because we still see your code. Yeah.
Yeah. Sorry, sorry. I was on my whiteboard again. Sorry. So I will repeat it. So just so it's here. So again. The average has to converge to the expectation value. That should be distributed around the expectation value. If you actually make a measurement of n of these random variables and sum them up, take the average of them, it should converge to the expectation value. And it should, the approximation must become better and better. Yeah? And you have to divide it by sigma squared over n. We will understand next week. We will understand where this comes from. The number in the denominator. Well, the background is basically that the variance of IID variables is additive. So the variance of x1 plus x2, that's the sum of the variance x1 plus x2. So that's basically twice the variance. And that's behind this approximation. One final thing for today that I wanted to discuss for today is what if I don't want to have want to draw from a uniform distribution? Yeah, so let's say so usually it's called like this. It's a uniform distribution over the interval 0 to 1. So this is clear. What if we have a more general distribution? Let's assume we know the CDF of the distribution. So we know this, and now we have this. This could be, for instance, this CDF. So that's the probability that the random variable is less than or equal to a given number x. And I will discuss this only for the case. I think there's a question that distracts me now, so I will try to answer this later. So if f is monotonous, yeah. So the CDF looks usually like this, yeah. So if f is invertible, which basically means that it's strictly monotonous. Oh, sorry. We can do it this way. Draw U from a uniform distribution. On 0, 1. And then set x equal to f to the -1 of u. So to the inverse of u. This will give nice values from that are distributed according to the cumulative distribution f of x. Now, for instance, let's assume that we have a random variable that is exponentially distributed. The CDF is also an exponential function, and then you take a random number and take the logarithm, and then the logarithm will follow an exponential distribution. So that's possible to draw from other distributions, but of course it's in many dimensions it's a very complicated problem. Yeah, sorry, I'm not quite through with my program, but I guess I should stop now here for today, and next week we will be a little bit faster, because then I will prepare some slides for it. I think that's better for the rest of the program. So I think I should stop here for today and answer some questions if there are any.
Okay. There is a question in the Q&A, and that's I think is an interesting and philosophical question. And it's, what makes a generator deterministic and truly random?
Okay. I see that Ilya wants to answer the question.
No. I just pressed that the question disappears. Yeah, no. You answer the question.
Okay. Yes. Yeah, I think that's contradictory. It will not be truly random if it's deterministic. Yeah? For me, that's mutually exclusive. It's truly random, but in a way, it appears truly random. So you cannot, in a way, it's perfect. It would be kind of truly random if you cannot predict it. But you can, yeah. For instance, for a Mersenne twister, if you know the previous numbers, you can predict it. But you don't see a real law or a simple law governing the behavior.
Okay. And I think there was one more, a couple of technical questions in the chat. Okay, so let me start from the last one. And where do we diverge from standard probability theory into the Monte Carlo methods?
Sorry, I don't see the question, but
it's in the chat.
Yeah, okay, sorry. So actually, we do not diverge, but we make use. So in Monte Carlo methods, we make use of standard probability theory, of several results of standard probability theory. For instance, what we use is that the expectation. So that's one of the inputs. So this, if these are IID, then this will be just n times the expectation of one of these random variables. That will be all. And the expectation of or the variance. This is a thing that you can show easily if you know some standard probability theory. The variance of the sum, that will be the n times the variance of one of the variables. And this means, so we can call this n times sigma squared. This is the variance. This is n times mu. And if we want, for instance, the average, for the average, we divide this by n. The variance of a variable that is divided by n, this will be 1 over n squared times n. So this is this means that the variance of the average value will be the variance of a single random variable divided by n. And this is what I corrected a few minutes ago. The ingredient of the central limit theorem. This is quite an important input to Monte Carlo methods. That because this is we can regard this as the error of the average as an approximation for the expectation value. And the error, so this is the error of the average, or the square of the error of the average. And this squared error is getting smaller and smaller with n. The squared error has to be divided by, or the variance has to be divided by n, and this the standard deviation, that will be the square root of the variance. So this is just the standard deviation divided by the square root of n. So this is one important input, maybe the most important input from standard probability theory to Monte Carlo methods. So in a way, we don't diverge, but we are applying standard probability theory to Monte Carlo methods.
Okay, thank you. And I think there is one more question about the pseudo-random number generators, and it's x of k is equal to what is the value of k? I think it's in the when you describe the procedure of pseudo-random.
Yeah, okay.
And we still see your handwriting, so probably you might need to switch to your code.
Yes. So the question was probably here in this part.
Mm-hmm. I assume so.
So this is the iterations. The first Python is starting with 0 as the first value. The first value will be 1, and then I fill the loop. So this x of 2 will be the previous value. In this case, for the first iteration, it's 1. The previous value divided multiplied with this, and then taking modulo this value to the power of 31. So this is just a loop index. If I want to running from 0 to 9,999.
Okay. Thank you. And I do not see any more questions, neither in the chat nor in the Q&A. I suggest that next time people focus more on the Q&A because it's easier to track the Q&A question than the chat questions, because in the chat there are also some generic comments. Okay, over to Francesco.
Okay, then Uwe, then it is my pleasure again to thank you very much for this very nice introduction to Monte Carlo methods. And I'm sure that everybody is keen to hear how the story develops next week. Yeah. So, and we will meet again in this using the same Zoom link also next Tuesday at 3 p.m. Not the usual 2 p.m. time because of constraints of our speaker, of our lecturer. Yeah. So Uwe, thank you very much again. So we wish you a warm evening in the snowy Germany. If it is still
stopped to snow again, yeah.
Okay. Okay. If it's some kind of consolation, it is raining here. No,
Yeah.
not. So thank you very much, Uwe. And thank you to all the participants to stay with us, who stayed with us until the very end. And we are looking forward to see you next week. And in the between now and next week, we will post online the video and the materials that Uwe kindly agreed to share. So Uwe, again, thank you very much. And Ilya, thank you for moderating the questions, and a big thank you to all the participants. Thank you very much. Have a good evening.
Yeah, thanks to all from me too.